Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. In the last lecture, we looked at how any arbitrary image can be decomposed into a set of plane waves, right? We said the image can be decomposed into some spatial frequencies, and those spatial frequencies are essentially the plane waves, okay? And we drew the analogy between the spatial frequencies and the traditional frequencies that we know. And then we also looked at how if some of the frequencies are attenuated, how that leads to loss of resolution. Okay. So in this lecture, the plan is to try to tell you about how the plane waves are generated. We'll look at that, and after that, we will do some numeric problems. All right. So to get started, so how are the plane waves generated? Well, I mean, if you studied electromagnetism, it would not be surprising to you that these plane waves are generated whenever you have oscillating charges. Okay. So essentially, whenever you have a dipole, oscillating dipole, you have generation of electromagnetic waves. So, and the electromagnetic waves cover a broad spectrum. We briefly mentioned it in a couple of places, but essentially you have the visible spectrum, which is which typically goes from about 300 nanometers to 700 nanometers. That is a visible part of the spectrum that you see around. But then there is an important part of the spectrum where, below the UV, ultraviolet, is, very short wavelengths, and those are useful. We mentioned the lithography applications where we use the ultraviolet light. And another important part of the spectrum is IR, so infrared, beyond the red. Okay, so essentially this part of the spectrum. Again, this is larger wavelengths than the red, which is 700 nanometers in this case. And we have what is called as near IR, which extend up to roughly around 1.5 microns to 2 microns. And then we have the mid infrared from 2 to 5. And then we have the long wave infrared, which is beyond that. All right. So we have this spectrum, various wavelength scales. And the beauty of Maxwell's equations is that even though the wavelengths are different, we say that the Maxwell's equations are scale invariant. That essentially means that the equations themselves remain same. Only thing that changes is the permittivity and the permeability. And we will talk more in detail about this in the next week. All right. So for now, let us say we have a plane wave like this. Before we talk about how they are generated, let me also introduce a couple of units. So you see on the bottom here, you have the nanometer units. On the top, you have the energy units. And if you look at any chemistry related subjects, you might also see another set of units called as wave numbers. Wave number, or they are represented by a unit which is centimeter inverse. So all of them essentially represent energies, okay, or the electromagnetic waves. So it is useful to actually know how to calculate between them. Okay, various communities use different units. So for example, how do I calculate the wavelength from, let's say, nanometers to EV units? Okay. So what happens is, we know the electromagnetic energy is essentially E is basically h nu. Nu is the frequency, and that is C by lambda. So we can write energy is hc by lambda. So what is energy associated with a wavelength, let's say, of 632 nanometers? I'll just consider a wavelength lambda equal to 632 nanometers. And I want to find out what is energy associated with this. So I'll simply write out the Planck's constant here, 6.63 into 10 power minus 34 and 3 into 10 power 8 divided by 632 nanometers. Okay. And if you calculate this, it will turn out to be some number. Okay. And roughly it will be of the order of 10 power minus 19 joules. But we don't find it convenient to talk of joules every time because it's 10 power minus 19, right? So we use another unit, which essentially, we take the energy in joules and divide it by the charge. Okay. So what I'll do is I'll say energy in EV is simply energy in joules divided by 1.6 into 10 power minus 19, the charge of the electron, and that gives me the energy in EV. So if you calculate this for this particular lambda equal to 632, this energy in EV will turn out to be roughly 2 EV. Okay. The reason I know this is there is a very simple formula that we all remember usually. This is 1.24 divided by lambda in micrometers. Okay. So if you want energy in EV, I'll say this is in EV. Okay. You want energy in EV, take the wavelength in micrometers and divide 1.24 by that wavelength. Okay. So in this case, this would turn out to be 1.24 divided by 0.632 microns, and that will be roughly about 2 EV. Okay. And I mean, I would suggest that you should be familiar with this because many times we use it. The other unit I mentioned, right, centimeter inverse. So the wave number. So what we do for that is, let's say I want wave number in this centimeter inverse. If you want this, what you do is you take 10,000 divided by wavelength in microns, lambda in micrometers. Okay. So for this, let's say if I want to know what is the wave number associated with lambda equal to 4,000 or nanometers or 4 microns. If I'm looking at that, then it will be 10,000 divided by lambda in micrometers. So that is 4 microns. So this is 2,500 centimeter inverse. It turns out that the centimeter inverse or the wave number units are used more in the IR. Okay, whenever you talk of let's say absorption in IR, we use these wave numbers. All right. So this is about the various wavelengths, and I mean these are some of the common conversions we use. So I just wanted to mention this here. And the energy and the wavelength are not just associated with the electromagnetic waves only, but you can also ascribe a wavelength to an electron as well. Okay. We mentioned, I mean, you must be definitely familiar with the de Broglie principle, which says that any matter wave has a certain amount of wavelength. And if you look at how much is the wavelength of a electron, let's say I have an electron with energy of 100 keV. If I can calculate the energy of electron, and it will turn out to be something less than 1 nanometer. Okay. And that has a very significant implication actually. There's a practical implication. In the last lecture, we had shown one image of this image. I said, these are the FinFET structures, and the size of these structures are roughly, in the order of nanometers, I said. But how did we make this structure? How did we take this image? You can't take an image with a regular microscope because of the diffraction limit, right? Because the features which are very, very small, of the order of 10 nanometers, their spatial frequencies are very high, so they will get attenuated. So how do we end up taking these pictures? Well, we do that using what is known as a scanning electron microscope. Scanning electron microscope, SEM. So in this case, what we do is we take an electron beam, we focus, we accelerate it to high energies and then focus it. And with that, we will be able to actually capture images, and that is used routinely in the nanotechnology world. Okay. So yeah, this has some practical implications of how the energies are. Okay. And I'll probably give you one small example in the assignment. Please take a look. We'll also give you the expression so that you can calculate and compare. All right. So now we understand how to denote various, how to express wavelengths in various units. Okay. So you should not be surprised in some papers when you see that, they're actually, let's say, scanning wavelength and they mention the units as EV. Some place they'll say nanometer, some place micrometer, some place centimeter inverse. All of them refer to the same thing. Okay. You should be comfortable in converting from one unit to other. There are several calculators available online as well which do this, but I would suggest that you should do it once to get familiarity. Okay. So now moving ahead, we said that the electromagnetic waves or the plane waves are generated by oscillating charges or oscillating dipoles. So the way this happens, I mean, if you have studied already the antenna theory, you should be familiar with this. But just as a recap, so let's say I have a dipole which consists of a positive charge and a negative charge. And they're fixed in time, what happens? Well, there will be an electric field which is in this shape. Will it produce a magnetic field? Will a dipole, or rather you have two charges which are separated by a distance, will it have a magnetic field? Will it generate a magnetic field? So think about it. You'll see that the answer is no. The reason for that is, according to Maxwell's equations, the curl of H, the magnetic field, is dependent on the change in the electric field with time. So if you have time varying fields, then you have magnetic field. If you have time varying electric fields, then you get magnetic fields, and so on. So now what happens if you just have two charges? Well, you will have electric field lines going from the positive to negative charge in this fashion, and they'll be spreading out. And these charges are not just fixed, they're going to oscillate. So these arrows are simply intended to convey to you that there is motion of these charges. And when they move, what happens? Well, the field lines have to move. Okay. The reason for that is, there is a very fundamental principle that the electric field lines, right? E field lines cannot cross. Why can they not cross? Any guesses? So I have some students here. So let me just ask them. Why do you think the electric field lines cannot cross? Any answers? So what I'm trying to say is, let's say I have an electric field line like this due to, let's say, dipole. Okay. And then can I have another electric field line like this? Okay. Two intersecting charges, two intersecting electric field lines. Well, it is not possible. The reason is, we'll have to go back to the fundamental idea of what is an electric field. Electric field is simply the direction in which a positive charge will move when placed in such a field, right? That's the basic idea behind an electric field. Now, if I have these two intersecting electric field lines and I place a charge, let's say I'll put a charge in this positive Q, which direction will it move? It cannot, of course, move in two different directions simultaneously, right? It has to move in a particular direction. And so we can easily see that electric field lines can never cross. So now, when my charges are moving, in this case the dipole, the distance between the electric and the positive and the negative charge is reducing. So immediately the field is becoming closer. Okay, and we should also remember this is a sinusoidally varying field. Okay, or rather dipole. Let's say I'll denote my dipole as P of t. The change in the dipole moment is simply going to be P naught cos of, let's say, some frequency omega t. Let's say this is the z cap direction. Okay, in the normal direction. So this is varying as cosine. So what happens is the charges will move very fast initially, and then they reach to maximum velocity, stop, change direction, go to the other side. So the velocity also oscillates. You have a large variation in the middle, and then once it goes to the edges, the velocity reduces and it stops, and then reverses the direction. That's what a sine wave tells you, right? So when you have such a scenario, you will see that the electric field lines which were originally here, they will start traveling as well. The phase fronts will travel, and then they'll again come. So the moment when they come close to each other and cross, for example, I'll have a scenario where the positive charge has gone down here and the negative charge has gone up here. The field lines cannot cross, so you'll have one oval that is generated, and then it just keeps propagating. And that is how you see that this is basically at, let's say, time t equal to 0 on the left, and then at a short time. And then if you go longer and longer in time, I have these phase fronts that are getting generated and they're propagating. Okay. And we'll also see that there are two regimes. One we call as a near field regime, which essentially means that the distance is less than lambda. We usually call it as a near field. And the far field regime, where the distance from the, let's say, the source of the field, right, is larger than the lambda, then that is usually called as far field. And it turns out that in the near field, you usually have only electric fields, because you have to have some certain oscillations that are happening. Electric field has to go to a P, come down and back. Only when that variation happens, you have a magnetic field getting generated. So in the near field, you usually have only electric field lines. But when you go a certain distance away, let's say lambda or more, then you'll start seeing that magnetic field is getting generated. Okay? And this process repeats. Essentially, these dipoles keep moving back and forth in this fashion, and they generate these electromagnetic waves. Okay? And of course, it should not be a surprise to you that in the normal direction there is no field. Not in the normal, but along the dipole you don't have any field. But in the perpendicular directions you have the field. This is a familiar pattern for some of you, definitely. Okay. And why do we call it a plane wave? It looks, it doesn't look like any plane wave, right? In the previous picture we had this perfect phase fronts. And here it doesn't seem like it is a plane wave. Well, the reason this is plane wave is, if you look at the fields, these black lines are the fields and the green are essentially the magnetic fields. So they're out of plane. They're going in and out of the paper, or rather the screen here. So you see that the electric and magnetic fields are perpendicular to each other. Okay. E is perpendicular to H, right? And if you go far enough, this phase front essentially is becoming straight. Okay. So if you go, let's say 100 lambda away from the source, and the phase front effectively becomes a plane. Okay. The electric field and magnetic fields are essentially confined to the plane, and they're varying with time, of course. So that is why we refer to this as a plane wave. Okay. And the source of the plane wave is an oscillating dipole. All right. So I hope that is clear. Are there any questions? Well, no. Okay. All right. That's fine. So let's move ahead. So yeah, we will talk of these dipoles usually, in nanophotonics, many times we say, okay, there's a dipole source. What we mean by that is, okay, we just put that oscillating charge and that is generating electromagnetic waves. Okay. And usually the dipole is given by this expression. Let's say it's there's a dipole moment and that is varying with time. Okay. And if you calculate once we have the electric and magnetic fields, we can calculate the Poynting vector. The Poynting vector, it turns out, will be of this form. You have some terms, additional constants, but there is this sine square dependence. So if you look at the way the energy flux happens, if you have this Poynting vector is simply E cross H. Okay, you have the electric and magnetic fields, and we saw that already they are in the out of plane and along this along the screen. So in the perpendicular direction is where the energy is propagating, right? So in this previous case, we see here that electric field is in this direction and then the perpendicular direction is the magnetic field. So E cross H will be in this direction. Okay. So if you look at that, it turns out that it's not a surprise if you look at the three-dimensional image. If I place a dipole in the center of this donut here, so along the axis of the dipole you don't have any radiation, but in the perpendicular direction you have this. So this forms this famous donut pattern. Okay. And that you can easily see, because if I think of this as an angle, observation point theta, along that dipole you have theta equal to 0, so there is no energy flux. But the moment I go to theta equal to 90 degrees in the perpendicular plane, I have maximum electromagnetic flux energy. Okay. And the important thing here is, one is the sine square dependence. The other important feature is that we have 1 over r square dependence. Okay. 1 over r square means it's as a function of distance, the energy flux is reducing, right? How does it make sense? To understand that, what we have to do is, let's say you have a source. It's emitting in free space. Okay. Then if you go to larger and larger distances, why is the flux density reducing? Does it make sense? Well, it makes sense because you have to think of, let's say, one sphere, let's say, centered around the same point. Okay, I have one sphere like this, and if I integrate the energy, total amount of energy on that sphere, so the surface area of the sphere is going to be 4 pi r square, and then I have at each point I have r square, 1 over r square, so that cancels out and the overall integral is going to be constant. So because of this 1 over r square dependence, the amount of energy that is propagating remains, the total amount of energy is constant, which is what it should be, because there is no absorption. You can't simply have the energy decaying over, long distances. So that has to be 1 over r square here. Okay. And then there's another important thing, that it has an if I take the time average power, it turns out that it depends on the fourth power of frequency, right? Fourth power of frequency, it's omega power 4. And then there is a second power of dipole moment. Okay. So these are a couple of important features that we see for dipole radiation. Okay. So this is what I just wanted to mention before I move on to the next section, which is essentially, I want to solve a couple of problems to get you familiar with the idea of some of the basic concepts we discussed in this week. Okay, so I would encourage you to pause the video and try to attempt these problems. And if you're not able to, you can of course just go through the video and I'll try to explain to you as I go along. Okay, the first exercise problem I want to look at is, let's say we have a beam of light with a wavelength of 532 nanometers, which is incident on an air glass interface from air side. Okay, what is the wavelength of light in the glass? Well, I mean, we looked at this problem already. We showed the simulations when we talked about the dispersion relations, but we just want to calculate. Okay, the answer is fairly simple, but I just want you to go through the motion. Let's say I have my lambda equal to 532 nanometers, and this turns out to be the green wavelength. Okay, green is centered typically around 532, even 515, and so it will be slightly different shades of green, but generally let's take the 532 to be green wavelength. Okay, when I have 532 nanometers of green incident on this, what will be the wavelength in the second medium, in the glass? Excuse me. So in glass, we already know whenever your refractive index increases, the phase fronts come closer, right? So we showed this simulation already. So this was the wavelength. So the peak in the center of the blue, I'll take the peak here and the peak here between one period is essentially the wavelength. Here the period has reduced, so the wavelength has reduced, and we already know the answer. So lambda in the medium, let's say I'll call it, let's say glass. Okay, lambda in glass is simply 532 nanometers divided by 1.5, and I think this will turn out to be about 350 nanometers or 350 nanometers roughly. 350 into 3, well, yeah, something around that. Okay, so now so what does it mean? The wavelength is changing. So I said, I mean, if you look back, you would have seen that 532 is green and 350 will be roughly in the violet range. Okay, violet. So does green light, is it incident on a medium, does it become violet light? Well, that is not true. Okay, because it also doesn't make sense. If I think of one block like this, let's say I'll take a block of glass. Okay, and then I'm coming onto it with, let's say, 532 nanometers. And the moment I go into this, it cannot become, the wavelength or it cannot become, the green light cannot become violet light. Okay, and when you come out, it cannot again become green. Okay, it's at least if you have, the regular linear materials, it cannot happen. If you have non-linear materials, some of these things can happen, but that's much more involved process. Okay, so what is happening? And we already said when we discussed the dispersion that the frequency is a property of a source, and that doesn't change just because your the light is incident on a medium, right? So how do you resolve this? Well, the way to resolve this, there are multiple ways to look at it. We already talked about it, we said that lambda naught, the free space wavelength, is nothing but, or rather, I have the free space wavelength which is given to me. Let me try to calculate the frequency. Okay, the frequency is simply c by lambda naught, right? So now, what happens when you go into a medium? Two things happen. One is the frequency reduces by n, and the wavelength also reduces by n, right? Lambda naught by n, and because of that, the overall frequency remains the same as it should be. Okay, the frequency remains same, right? Frequency cannot change just because I'm incident on when the light is incident on a particular medium. All right. So this is how it is. So I just wanted to re-emphasize this point. I hope this is clear. If it is not, if you have any more questions, feel free to attend the interactive sessions and we'll try to address it further. All right. Okay. So let me now move on to the next exercise problem, which is given here. So basically you're asked to consider a 1D electromagnetic wave, which is given by a certain expression here, and calculate the amplitude, wavelength, time period, and phase velocity of the wave. Okay. These are simply to get you familiar with the idea of, representing these electromagnetic waves. That's all. The idea is only that. These are fairly simple and you should have done it in some of these basic courses. Okay. The first thing I want you to notice, the electric field is now not just a scalar, it is a vector with a direction here in this y cap. Okay. And then, so the first thing when you look at this expression, what you have to consider is, what is the direction of propagation? Okay. Direction of propagation. What is it in this case? Well, it is varying. Basically, what is the coefficient of k, right? So it's x direction. So direction of propagation is x here. So along x it's propagating. And what is the polarization? Polarization means what is the direction of electric field? Okay. In this case, the polarization is y cap, y direction. Okay. So we have this electromagnetic wave. Now, what is its amplitude? Okay. Let's say my amplitude. So is simply the coefficient of the cosine term, right? So in this case, E naught is simply going to be equal to 10 volt per meter. Okay. This is the amplitude. And what is the wavelength? Wavelength. There are multiple ways of calculating it. If you know the speed, then you can calculate from the frequency. But in this case, we are anyway given k. So my k is given as 6 pi into 10 power 6. Okay. And that k we said is 2 pi by lambda in the medium. Okay. So now irrespective of what this medium was, lambda is going to be equal to, if I cancel out this, then it will be 1 by 3 into 10 power 6. That will turn out to be equal to 0.33 micrometers. Alright. So what is the wavelength? Wavelength is 0.33 micrometers. Okay. And the third thing, what is the time period? Time period of oscillation, right? And that is of course related to the frequency. So we know that omega, right? The angular frequency is 2 pi by the time period. So what is my angular frequency here? It is simply the coefficient of t. So that is 8 pi into 10 power 8. So it turns out that time period is going to be 2 pi is going to go here, 1 over t is going to go there, so 2 pi, so 1 by 4 into 10 power 8. Okay, it will turn out to be some number. Okay, this is 0.2, 1 by 4 will be 0.25, 0.25 into 10 power 8 seconds. Okay, that is the answer. So that is, 2.5 nanoseconds. All right. The last one is the phase velocity. I think I missed emphasizing this when I discussed the dispersion velocity. Okay. So we define for any electromagnetic wave, we can define what is known as phase velocity and also group velocity. The phase velocity is the speed which is the phase fronts propagate. But the energy can actually propagate at a different velocity, which is called as a group velocity. Okay. And if you take a simple electromagnetic wave with linear dispersion, it turns out that those are similar. But if you have a guided mode, in the dispersion diagram we had shown one mode which is in the beyond the light line. There's a mode which was going at a particular, it exhibited a certain dispersion. In that case, the group velocity will be d omega by dk. Okay, we will come back to it in some of the later lectures. So for now, let's just focus on the phase velocity. And the phase velocity v phase is going to be simply omega by k. In this case, my omega is what it is, 8 pi into 10 power 8 divided by the k is 6 pi into 10 power 6. So that turns out to be 2 into 10 power, 200, right? Am I right? Oh, no, not 200. This is 4 by 3 into 100. So 400 by 3. All right. Meters per second. So 133 meters per second. Okay. And finally, of course, I said, we can talk of group velocity, V group, which is d omega by dk. And if you take a simple linear dispersion omega equal to ck, this will turn out to be Vg also is going to be c here. But the dispersions can be different. Sometimes they are not linear, then the group velocity becomes more interesting. All right. Okay. So this is the second problem that I just wanted to discuss quickly. Any questions? Any mistakes I have done? So usually I have a tendency of making mistakes. So, that happens, because, yeah. All right. The third exercise problem I wanted to talk quickly was this. So in this case, you have a uniform plane wave with electric field given in a certain direction, which propagates in a lossless medium in the positive z direction. And Ex is varying sinusoidally with some frequency and some maximum value. Okay, so if I So it is t equal to 0 and z equal to 0, it is 5 volt per meter. Give the expressions for instantaneous electric and magnetic fields. Well, that's interesting. So basically we already saw that E is going to be E naught cos of, I think we always use this expression. So in this case it is propagating in the z direction. So it will be kz minus omega t. Okay. Now the question is, what is E naught? E naught already is given. The maximum value is 5 volt per meter. So no surprises there. So this is going to be equal to 5 volt per meter. What is K? And what is omega? So let's handle first omega. If I have my P, omega is basically in this case going to be 2 pi times the frequency, which is 100 megahertz, right? So this will be 100 megahertz. So 2 pi into 1 into 10 power 8 radians per second. So 2 pi into 10 power 8 radians per second. So this is my the omega. All right. Now my wave vector k, what is this going to be? How do we calculate? Well, we know that omega is basically c by n times k. If you have a certain refractive index. Why do I take refractive index here? The reason is we are given that this medium is epsilon r is 9. Okay, and we already saw that n is equal to root of epsilon r. So in this case the refractive index of the medium is 3. So my velocity of the wave is going to reduce by that. So I am putting this factor. So now my frequency is going to be this, and so this k is the k in the medium. Okay, and this is the velocity of the wave in the medium, right? Velocity, which is reduced by the term by the factor n. So we know what my frequency is, and we know what my c by n is, right? So what is this going to be? K is going to be omega. Okay, let me try that. K is going to be omega is n is 3, and this is going to be 2 pi times 10 power into 10 power 8 divided by c, which is 3 into 10 power 8. So that is going to be 2 pi. I mean the units are meter inverse for k. All right. So this is my second item. So once I have these values, I can easily put back this into the expression, and I'll have an expression for the electric field. I won't do that, but yeah. So now this is the electric field, right? So we put back the k and omega, and that's it. We have the answer. Now what is the magnetic field intensity? Well, we know that I didn't mention it, but I hope you're familiar with this. The ratio of the electric and magnetic fields is given by the impedance of the medium. Okay, and this is simply going to be 120 pi is the free space impedance, or eta naught, what we call as, divided by the root of epsilon r. Okay, in this case we are not having mu. Okay, by the way, if you have mu also, mu relative is 1. If mu is not 1, then it makes some difference, some variations. But right now let's assume that it's a simple dielectric. Okay, so now my ratio of electric and magnetic fields is going to be equal to this root of 9 is 3, so this is going to be 40 pi. Okay, so now what will be my magnetic field? I can simply write out the expression. I can say that magnetic field is going to be my electric field was 5 volt, so 5 divided by 40 pi. 5 divided by 40 pi into cosine of my kz minus omega t, the same thing remains. The only issue is, in this case we have said that in the beginning we said this is x cap. Electric field is in the x direction, so x polarized, and the direction of propagation is z. So it's important to specify that my magnetic field is going to be in the y cap direction. Okay, it has to be that. Otherwise, because we know that electric and magnetic fields are going to be perpendicular, and they both simultaneously are going to be perpendicular to the direction of propagation. So because of that, we can write out this expression for the magnetic field. Okay, and okay, the last part is determine the locations where Ex is maximum at t equal to 10 power minus 8 seconds. Okay, so electric field is maximum. Well, electric field is given by a cosine expression. So this E is maximum when the argument, right, of the cosine, which is simply kz minus omega t, is equal to 2n pi. Okay, this n is basically, okay, I should not call it n, maybe I'll call it m, because n can be confused with refractive index. Okay, so 2m pi. So if I have 2m pi, now my time is basically 10 power minus 8 at t equal to 10 power minus 8. Let's substitute the k and the k and the omega. So what will that be? So my k is simply 2 pi. So 2 pi into z minus omega is 2 pi into 10 power 8 into time is 10 power 8 minus 8 given to us. That should equal to 2m pi. The 2 pi's will go. So what you will end up seeing, z is going to be equal to, you can take it to the other side. So 1. Okay, by the way, this cannot be only m is an integer. So it can be plus or minus. So yeah, 1 plus m. Okay, this m is an integer. 0 plus 1 minus 1 and so on. So these are the locations where your electric field is going to be maximum. Okay, why do I do this? Well, the reason I'm going through this, these are seemingly, I think straightforward problems which you will see in any electromagnetics course. The reason I'm trying to emphasize this here is some of these things can be verified in a simulator. Let's say you're trying to simulate some of these nanophotonic structures. These are some sanity checks you can do. For example, let's say have a plane wave incident on a medium and look at the wavelength. That will be the first sanity check you will do. Okay. Similarly, you will look at the magnetic field directions, electric field directions. You can plot out these quantities. What is the electric field in the x direction, in the y direction, and so on. You can plot out, and this will be a very good sanity check for you. All right. So now, the last problem for this week I want to look at is this. So let's now consider a plane wave which is propagating in a particular direction, which is let's say 30 degrees with the x-axis, and it also makes 90 degrees with the y-axis. So give the expression for representing the field. So now, so far we have looked at plane waves which are going in one single direction. Now we want to look at two different directions, and we kind of looked at it in the discussion about oblique incidence. Okay. So now what we are saying is, let's say you have these three axes, x, y, and z. X, y, and z. Okay. Now we are told that the electric field makes the wave is propagating in a direction that makes 30 degrees with the x-axis. So my wave is going in this direction. K is the vector. So this is 30 degrees with the x-axis. And it also makes 90 degrees with the y-axis. So that means K is essentially confined, right? Wave is confined to xz plane. Okay. Excuse me. So wave is confined to the xz plane. So now how do we write the expression for the electric field? Well, now since we have a general case, we should recall that electric field now is going to be E naught. I'll write out the general form I k dot r minus omega t. Okay. What essentially it means is we have to take a dot product of each of these k's with the position vector r. So what is going to be my kx? Kx is simply the component of k, or rather I'll call it maybe k naught. K naught in the x direction, that is simply going to be cosine of 30 degrees. Cosine of 30 degrees is root 3 by 2. Root 3 by 2 k naught. What is ky? Since it's 90 degrees now, there is no component, so this is going to be 0. And kz is going to be the cosine in with the z axis, right? So that is 60 degrees there. So this is the okay. So k naught cosine of 60 degrees. That is going to be 1 over 2. Okay, these are the components. So now what is the expression for electric field? Well, this is slightly ambiguous here. The reason is you can have two possible directions for electric fields. Okay. So what we say is, for example, here the electric field can be directly in the direction of y here. That is going to be normal to my k, and that is a valid answer. Okay. You can also have a scenario where electric field is perpendicular to this direction. Okay. So this was, let's say, 90 degrees, right? Sorry, not 90. I should say this is 30 degrees. The k is 30 degrees with x-axis. I can think of electric field in the 120 degrees from x-axis location. That is also going to satisfy Maxwell's equations. Okay. That is also a different electric field that is possible. And so we say that if you have a normal plane wave, you can have two possible polarizations. Two polarizations possible. One is E is along the x direction, in the y direction. Okay. Electric field is along y cap. Okay. That's one polarization that is possible. So in this case, my electric field expression turns out to be quite simple. So my E is equal to E naught exponential I k dot r. So kx x plus ky y minus omega t. All right. This is, and then there is a direction vector associated with that. This is y cap. Okay. So it is in the direction of y. I'm sorry. Yeah. This is one possible electric field that is there. You can have another possible electric field polarization. E field is or rather makes 120 degrees with x-axis. With respect to x-axis, there is 120 degrees. So that is also, but in the xz plane. Okay. And in xz plane. Okay. When you have that, of course, you can write out the direction vectors. Rather, you can calculate the components in different, x and z directions, and you can write out this expression. Even this vector is not going to be y, right? It's going to be two parts. There's going to be some field along the z axis and some field in the x axis. Okay. So these are the two things. Okay. If you now think of, just an extension there, just to think of this, no? The electric field was very simple in the y cap. What will be the, if you want asked to write the expression for magnetic field, what happens? If the electric field is in y cap, in this case, I can think of a magnetic field which is going to be in the direction, so it's going to be confined to the xz plane. So this will have a component in the x cap and z cap direction. Okay, the magnetic field is going to be in both these x cap and y cap, z cap directions, right? Because it simply has to be perpendicular to the both the direction of propagation and the electric field, which is in this direction. So it has to be in this 120 degrees, right? So that will have two components. Or if you choose a second case where my electric field makes these two components, right, x and z cap, then my magnetic field is going to be simple. So in this case, magnetic field will be in the y cap direction. Okay. So these are two independent polarizations that are possible for a wave which is propagating in a medium. So many times, these are two degrees of freedom that are associated. And in simulations, there are various terminologies people use. Some people call it TE, TM, by looking at, the plane of incidence, whether the electric field is perpendicular to it or the magnetic field is perpendicular, we call it TE or TM. Or in some communities, we talk of S and P polarizations and so on. Okay. Right now, I don't want to get into it, but these definitions are there, and sometimes we just have to, I usually don't remember them, so I keep cross-checking the definitions. Okay. So what is, transverse electric field is fairly straightforward. You have a plane of incidence, electric field is perpendicular. Okay. Yeah, this is one important aspect. So any questions about this? Yes, we have one question. Yeah. Okay, so I'm asked to go back to the EM radiation from oscillating charges. Yes? Yeah.
We see the second and third diagrams.
Mm-hmm.
So, in one field, even the dipoles are oscillating on the same direction. In one diagram, we have the starting from positive and ending at negative. In the third one, we are getting a circulating kind of thing. So, what is the difference between the two?
No, well, it just, it is, we are only considering, okay, this circulating thing happens when the charges cross each other. It's just a schematic illustration of what distances we are talking of, right? So when they cross each other, think of electric field. One electric field is attached to the positive charge. Okay, the question was, now why do we have here these circulating things and not in the second picture? Okay, so this I'm just trying to show you that how the electric fields are going to vary. Okay, as a function of position, right? How the things will vary. Once you come closer, then they will accelerate. So there's a very fast change and all that. So now why this circle is coming? Why these electric field lines are closing on each other? Well, if you have two lines which are crossing each other, you attach the electric field line starting from the positive and then going to the negative. As they cross, the electric field line cannot cross. So essentially they forms one circle and the next one starts. Next loop starts. Because they cannot cross each other, right? Think of, two charges which are tied up with some thread and try to cross. If you cross each other, then the field lines have to cross. That cannot happen. So that kind of, the loop closes and the new thing starts. And if you plot how the electric field changes at a particular position, you will see that it's going to be a sinusoidal wave. Yeah. All right. So this essentially brings me to the close of week 1 of the Nanophotonics course. We introduced some very basic concepts. In the next lecture, next week, we will look at how the waves interact with various materials. All right, and we'll also introduce some basic models for that. So, I'll see you next week. So, if you have any questions, please feel free to reach out to us. We are looking forward to it, and unless you ask us questions, we won't know how to respond. All right, so please do. Thank you so much for your attention. Take care.